All right, today we're going to be talking about one-to-one and inverse functions. So inverse functions you have definitely seen before because they're in Algebra 1. One-to-ones you have if you've taken pre-calc, but if not, it may be new to you. So definition for inverse functions. Functions are inverses if and only if f of f inverse is equal to f inverse of f is equal to x. Now, this right here, if you are asked to prove, show, or verify that two functions are inverses, this is what you need to do. You need to show that both compositions simplify to the original inside input, which in this case, in the original function, would be x. So this is one of our properties, but it's also the definition. So both compositions simplify to the original input. If you are asked to show that two things are inverses, verify that something you found is indeed the inverse, prove two functions are inverses, that is how we do that. The other type of function we need to know about in this section are one-to-one functions. And a function is one-to-one if no two different x's have the same y. So meaning if your x's are different, then your y's have to be different. And if your y's are the same, which is what this says right here, f of a equals f of b, that means if the y values are the same, then the x values had to be the same. We can tell if a function is one-to-one if its inverse is a function, which the easiest way to tell if you don't have the graph of the inverse is that the original is going to pass what we call the horizontal line test. Works the same way as a vertical line test, except that we're performing it on the original function to basically decide if the inverse is a function, because that's what will decide whether the function itself is one-to-one. By the fact that it's a function at all means the original already should pass the vertical line test. But if it also passes the horizontal line test, then it's a one-to-one function. So we already talked about the fact that both compositions have to simplify to the original input if they are inverses. Other two things that we need to know about inverses is that the domain and range are switched. So whatever the range is on your original function, that's the domain of the inverse. Then the domain of the original is the range of the inverse. So domain and range are just switched. Also, on the graphs, they should be reflections of each other over the line y equals x, which means that if we were to fold our paper on this line, which has a y-intercept of 0 and a slope of 1, so it's that diagonal looking line that's increasing that goes through the origin, we could fold it on that line and the graphs would line up on top of each other. So that's what it means to be reflections over y equals x. So this next part and final kind of summary piece of the lesson today is steps to find an inverse, which we did these in algebra. I'm going to walk through, and for some reason I called this function g, but in the directions I called it f. So let's rename it f for the convenience there. So in part 1, says find its inverse, f inverse, and check your answer. So here is how we're going to find its inverse. I'm going to color code my work today. So I've got purple here, and then my work's going to be in purple. So first thing I'm going to do is I'm going to put y in place of the function notation. So instead of f of x, I'm going to put y equals. Next, I'm going to switch the x and the y. Then I'm going to solve for y. Now, we've already talked about the old Western switcheroo, as I call it. If I have my variable that I desire in the denominator, I can switch the entire denominator with what's on the left side of the equation. Because remember, all that really is doing two steps in one. It's multiplying both sides by y plus 2 and then dividing both sides by x. So I have y plus 2 equals 4 over x. So then I would subtract 2 on both sides, which gives me y equals 4 over x minus 2. And the final step is to put it in our f inverse function notation form. So f inverse of x equals 4 over x with a minus 2. All right, the second part says check your answer. So this is where up at the top, if I said, it says verify, show, prove that they're inverses. Here we're checking that they're inverses, but that's the same idea. I have to show that f of f inverse simplifies to x and that f inverse of x does the same. So in this case, I've made f inverse my inside function. So I'm going to do f of this entire thing. So that means that in place of the variable in the original f function, I'm going to put in an x instead. So I have 4 over, in place of the x, I've got this, 4 over x minus 2. And then don't forget this plus 2 that was on the end. Now I'm going to simplify, and in the denominator I've got negative 2 plus 2, which is 0. So I've got 4 over 4 divided by x. So keep, change, flip, keep the 4, change division to multiplication, flip the second fraction. So I've got 4 times x over 4, which this is 4 over 1. We know these 4's can cancel each other out, so I've got x over 1, which is just x. So I've proven that f of f inverse simplifies to x. Now I'm not done checking my answer until I also show that f inverse of f simplifies to x. So f inverse of f of x. This time my original is the inside function, so I'm going to plug it in. So f inverse of 4 over x plus 2, which again means that I'm going to go and I'm going to put this entire fraction right here in this function of the inverse. So 4 over this whole thing, 4 over x plus 2, and then I've got a minus 2 on the end. So in this case, I need to simplify this whole thing first. So again, I'm doing the keep, change, flip. And I know someone had asked me in class that if you knew they canceled out, could you just cancel them? Yes, in this case, we know it's going to be 4 over 1 times x plus 2 over 4, meaning that we know the 4's are going to cancel, so that's fine. 4's are going to cancel, but you do need to write out the next step because that's going to give me x plus 2, and then I've got the minus 2 on the end. Then those cancel, and then I get equals x. What I do not want to see is you just hacking off pieces without actually doing the simplifying. So I only reduced one piece at a time, the only piece that made sense in each individual step. Okay, so I've checked my answer. That's the same thing as proving that two functions are inverses. I showed both their compositions simplify to x, which means I can feel confident about this purple answer because I know that it's right. So next, it wants me to find the domain and range. So again, we're going to kind of color code these today. So blue for that. So part B, my domain of f of x. So my original f of x is right here. And x is allowed to be anything except what makes the denominator 0. So that means that if it can be anything but what makes the denominator 0, that means x can't be negative 2. So it can go from negative infinity to negative 2, and then from negative 2 to infinity. The range of f of x means what can the y values equal. So this is a rational function, and we've learned things about rational functions and horizontal asymptotes and all of that. This guy has, because it's a transformation of 1 over x, it has a horizontal asymptote at y equals 0. So meaning I know that the range is going to be everything except 0. So from negative infinity to 0 and from 0 to infinity. Now, if you don't remember the horizontal asymptote rules as well, you could go ahead and go to the domain of f inverse instead. So domain of f inverse, if I look at f inverse itself, right here, x cannot be 0. So it means anything but. And the reason why I said you could do that instead of the range is because remember, one of the properties of inverses is that the domain and range are switched. So the domain of f inverse has to be the range of f of x. So if you find both domains, you can really just copy down the ranges from the other domain. So I know that the range of f inverse is going to be everything except negative 2. So negative infinity to negative 2 and negative 2 to infinity. All right. Next, graph f inverse, and y equals x on the same coordinate axes. Okay, so let's go ahead and do let me get a different color here. I'm going to use red for f of x. Now, this guy, if you recognize it as a transformation, you certainly could just graph it using transformations. If not, totally fine. You can pick some points to fill in. Now, I know from here that I'm going to have a vertical asymptote at negative 2 because this is a left shift of 2. So if I graph my vertical asymptote here for the original, and I know that the horizontal asymptote of the original is still at 0, so I don't really need to graph it, but that's where it is. So if I want to pick some values to make sure that I'm getting a good shape on my original, I would probably want to pick like negative 1, 0, 1 perhaps. You can pick things that are bigger, it doesn't really matter. So for f of x, I need some, I know the branches are going to be over here and over here, so I need some that are less than negative 2. So let's just say I'm going to do negative 4 and 2, 3, 4, negative 4 and negative 3. That gives me 2 points on that branch. and then I'm going to do -1 and 0 on my other branch. I can pick more if I want. So if I plug in -4 for x, that gives me -4 plus 2, which is -2. 4 divided by -2 is -2. So -4, -2 would be a point on my graph. So -4, -2. And then -3. I got 4 over -3 plus 2, so that's 4 over -1, which is -4. So, down right here. I should know what shape it's making, but if you're not sure, maybe pick -6 right over here. And if I did that, -6 plus 2 is -4. 4 divided by -4 is -1. So that would just give me an extra point to plot if you wanted it. So I can see that this branch should look about like this. And then if I pick up the -1, -1 plus 2 is 1. 4 divided by 1 is 4. So I have -1, 4. Then if I plug in 0, that gives me 4 over 2, which is 2. Again, if you feel like you need more points, I can pick additional points if I want. If I pick 2, for instance, let's say, so then I've got 4 over 2 plus 2, which is 1. Forgot to fill this guy in. So 2, 1 would give me a third point. And again, that gives me a really nice idea of what my graph should look like. Apologize for this little mishap there. Okay, now when I go to graph F inverse, you do not need to come up with a whole nother table because the domain and range are switched. I am not going to come up with this table. What I am going to do is I am going to simply use the table that I already had, and I'm going to give my value based on that. So let me switch to be like a darker green. There we go. So if I have F inverse of X, all I do is just switch these. So instead of -6, -1, I should have -1, -6. Instead of -4, -2, I should have -2, -4. So on and so forth. So you can go straight down the line, copying switched domain and range, and that will get you very quickly enough points to plot. So -1, -6 would be right here. And I do know from here that my inverse function has a horizontal asymptote shifted down to over here. So -1, -6, -2, -4. So -2, 2, 4 right here. And then I've got -4, -3, which would be right here. So again, I can see in green the asymptote. I'm going to have a vertical asymptote at 0 because that's what makes the function undefined. So if I draw this guy, should look something like this on this side of the branch. And then I know I should have another over here somewhere, and I've already got the points. 4, -1, 2, 0, and then 1, 2. I know it's not going to go cross the axis because x equals 0 is a vertical asymptote. Sorry, I'm having trouble using my online pen here to connect the dots. So now I've got my two graphs, my f of x in red, my f inverse of x in green. If I then go back and graph like it asks me to, y equals x on the same coordinate plane, starts at the origin, slope of 1. So it's this line. And I prefer to pretty much connect dots off the page if I can. I'm sure it's not going to help me draw this any better. It's hard to use these online tools, but sometimes it looks okay. There we go. It's not terrible. When you complete the graph, you have to make sure that your graphs do indeed look like, if you folded them on y equals x, that they would line up on top of each of themselves, which in this case, it definitely appears that way. And you can fold your paper if you'd like to test that out. Okay. Like I said, there'll be some things in your homework where all it's asking you is say, is this a one-to-one function? So you look at the horizontal line test and you say yes and no. Some of them might just say find the inverse. Some of them might just say graph the inverse. But here we've done an example where we did all of it. So hopefully that should make you feel confident to know what you're doing for the practice.